So now, as promised so long ago, we will find many diverse types of area very quickly. So here's an area from 0 to 2 of 2x minus x squared. So if I want to know this area, I just say, well, that area is the integral from 0 to 2 of 2x minus x squared dx. All right. Oh, I'm going to show you this nifty new notation too, okay? So first of all, we're going to find out what the antiderivative is. So the antiderivative of 2x, I'm going to raise the exponent 1 and make it x squared, and I'm going to divide by the new exponent. So really it's 2x squared over 2 minus, raise the exponent 1, divide by the new exponent. All right, that's my antiderivative. Now check out this groovy notation. I'm going to put like this, 0 to 2. Now what I have to do is this part of the theorem where I do the antiderivative at b minus the antiderivative at a. So what it means is I take the antiderivative that I found, I plug in the 2, and then I plug in the 0, and then I subtract them. All right, so this means plug in the 2, so I'm going to have 2 times 2 squared over 2. I mean, I could have reduced the 2s, that would make it easier, but I didn't. 2 cubed over 3. So I got to put in the top limit first, and then I subtract the bottom limit. 2 times 0 squared over 2 minus 0 cubed over 3. All right, so then this equals 4 minus 8 thirds, 4 minus 8 thirds. All this is 0, so it is, what is that, 1 and 1/3, right? All right, because it's 12 thirds, yeah, 1 and 1/3. Ba-ding. Easy peasy. So get your antiderivative. You make this notation right here. There are some different notations, but this one's the most common. The limits then go on to the right. The integral and the dx, we did an antiderivative, so the integral's not there anymore. And then we plug in the top limit, bajwing, plug in the bottom limit, bajwang, subtract, bajwing. Bajwing, bajwang, bajwang. All right, this one. I want integral from 0 to 4. I want the area from 0 to 4 of x cubed. You know, so we had to do so much work to get something like this when it was x squared and it was 0 to 2. Now we're just going to go like this. It's the integral from 0 to 4 of x cubed dx. That's the first thing, is to represent the area as an integral. Then we're going to say our antiderivative is x fourth over 4. Raise the exponent 1, divide by the new exponent. I put the limits over here on the right. Plug in the top limit, 4 to the 4th over 4. Plug in the bottom limit, 0 to the 4th over 4. All right, one of the 4's cancels, so I have 4 to the cubed, which is 64. 0, 0, so it's 64. That is how we do it. All right, so let's just do some more areas. Let's see, we did x cubed from 0 to 4. Let's find the area under, so find the area, we say under the curve. So I'm going to start with, I was going to do 3x squared minus 2x, we'll go plus 4, all right, from, I don't know, I'm just making this up, from 2 to 4, all right, I have no idea, just made it up. Okay, so if I want to find the area under that curve, I'm going to do, I don't even have to graph it, okay? I'm going to say the area is the integral from 2 to 4 of 3x squared minus 2x plus 4 dx. I do my antiderivative term by term. Raise the exponent 1, divide by the new exponent, 3x cubed over 3. Raise the exponent 1, divide by the new exponent, 2x squared over 2. Just like derivatives, a constant just stays in place. And just like the derivative of 4x would be 4, so the antiderivative of 4 would be 4x. So the antiderivative of a constant is always the constant times x. All right, and then I'm evaluating that from 2 to 4. So this one's going to be a little bit more work. I can at least cancel the 3's here. So then I'm going to have, let's cancel the 3's and go ahead and plug stuff in. So I'm going to have 4 cubed minus, cancel these 2's. So I'm going to have 4 squared and then plus 4 times 4, which is 16. And then I go minus. So then this one's going to be plug in the 2, cancel the 3's and I get 8, cancel the 2's and I get 4, minus 4, and then 4 times 2 is 8, so plus 8, and that's it. I just plugged in the top number, plugged in the bottom number, simplified a little. All right, the 16's cancel, so I just have 64 right there. I don't even need the parentheses, but I put them anyway. minus, gotta watch signs here. So I have 4 plus 8 is 12, right? Is that right? Yeah. So that is 52. That's the area under that curve. Boom. All right, here's one. Here's a fun one. Find the area under sine x from 0 to 2 pi. All right, so we're going to do the integral from 0 to 2 pi of sine of x dx. So that equals, all right, we already talked about the antiderivative of sine. Remember, you're basically going to look at you're going to look at your known derivatives, and you're going to say, I know that the derivative of sine is cosine. I know the derivative of cosine is negative sine. That means the antiderivative of negative sine is cosine. So the antiderivative of negative sine is cosine. That means the antiderivative of sine is going to be negative cosine. All right, so it's going to be negative cosine x. We're evaluating from 0 to 2 pi. All right, so this equals negative cosine of 2 pi. All right, that's our first one, putting the 2 pi, minus negative cosine of 0. All right, well, cosine of 2 pi is 1, so that's going to be negative 1, minus cosine of 0 is 1, so negative 1. Wait a minute, it's 0. How can the area under the curve be 0? It's an area. This is an area. How is the area 0? All right, here's what's going on. This is the graph of sine of x from 0 to 2 pi. Here's pi, here's 0, here's 2 pi. All right, so you know how we're finding all our areas by doing a delta x times an f of x sub I? All right, well, when you're over here, the value of the function is negative. Well, it's still f of x sub I. It's just negative. So what happens is these rectangles are counted by the integral process as negative. So what you really have is a positive area above the curve, and then areas below the curve count as being negative. Because the sine curve is symmetric about the axis x equals pi, it's symmetric about the point pi 0. That means that the positive area and the negative area are equal, and that cancels out and gives you 0. So what about that? What about this negative areas? You're going to find that there are a lot of applications where we want that negative area. We want to consider that area to be negative. So if we talk about displacement instead of distance traveled, what this means, this is what a pendulum does. If I start a pendulum, and I consider positive velocity to be this way. So if I release the pendulum releases, accelerates. When it gets to the center, the pendulum decelerates, all right? And then when it gets to the high end, it reverses direction and goes backwards. And it ends, so this is a negative velocity, means we're going back. And we end up in the same place we started. So what this object is doing is going to the right and then going to the left. It ends up where it started, so the displacement, how far away it is 0. So there are lots of other things, like this could be a conservative energy field. So for example, if I have a system that is gaining energy, and it gains energy at a certain rate, and then after time it starts shedding energy, losing energy, and if it sheds as much energy as it gained, then it's going to end up with a 0 gain. All right, this could be a financial system. It could be a business. This could be my business. This could be the money that I'm making, the rate of earnings in the business. So I'm earning money at an increasing rate. Then something happens and I start decreasing my earning rate. And then my earning rate becomes negative. So then what the area under the curve is telling me is that the net value of my company is now 0. Right. So often I want to count that area below the curve as negative. Sometimes I don't want to count the area below the curve as negative. And in those cases, I will have to separate the positive and negative parts of the curve. So that is a complication we'll have to deal with.